Okay. So the last thing, we had was, we had this, incredible theorem that, if an only there exists finitely generated, R submodel. A inside P such that use and this is very useful because we use this as a tool to show that sums and products of integral elements are integral. And so actually integral elements form. So if you have a ring extension T containing R, then the elements of T that are integral over R actually form an intermediate ring called the integral closure of R and T. Right. Theorem. What this means that function this would be like see if R is going to be closed, then so I'm not going to prove this later because I'm going to develop some stuff that will make this a lot easier than just going through element by element. So remember what this means. So what this means is if R is integrally closed, then this is integrally closed. So everything, the quotient field of this is K round bracket X, right? It's rational functions over K. Everything that is integral in KX is integral over RX. So X. And like I said, we're going to develop some stuff that will make this easier. But of course, notice how nice induction is. Because now this is integrally closed, so you can do its polynomial extension and so forth. And I'm going to skip the proof. The next one, theorem 9.9. Any UFP, and I'm more justified probably skipping the proof. This one is you all familiar with tourism? I was waiting to see if there has to be tourism. I like that. I even added it to my little latte cover because I'm just dying to use it. Tourism, you know what a corollary is, right? It's something that follows from the theorem. Tourism is something that follows from the result of proof, right? And this really, I think that this really is a tourism that we did. If you look back at the example I did where I proved that C was integral close, if you look back, what we really used was the fact that Z was a unique factor associated with it. Never did I use any specific properties of Z. And in fact, I used less than that, really. I really kind of just used it as great GCD domain. Okay. Now, I'm going to write one of my favorite silly lemmas. I like it because it's very silly. And you will laugh. Laugh when it's done. I show you the proof. And even though it's rather silly, it's actually kind of useful. It's going to crop up for us. So we do the following lemma that we're building to a thing. Use this later. 9.1.10. What are and T be domains? And U a unit of T. Right. And U inverse is over R, if and only if U inverse is in R of U. Okay, so let's prove this. And you'll, I think, appreciate what I mean about it's a little silly when it's true. Let's do this. Suppose the U inverse lives in R joint Q. So just write down what this means. This is exactly what it means for U inverse to live in U. But you guys see what our next move might be? Our goal is, of course, to show that U inverse is actually integral over R. And it should be N for N minus one. It doesn't matter. You mean the index here? Yeah. Yeah, it doesn't matter. I mean, this is arbitrary, right? Maybe I'll regret having not called it N minus one later, but we'll see. We can multiply both sides by U to the minus N, right? A0, U inverse, here, is A1, U inverse, A minus 1. Oh, this is So, inverse. Three, it's a U inverse is a root of this mind polynomial coefficients. Am I good with that? How about the other direction? Well, suppose. Really, all I'm gonna do is just engineer this in a direction. All right, this means you inverse, if I call it the same name polynomial down here. Minus a and minus one. You inverse minus a again is zero. Now just run it in the reverse, right? That should be plus. I've got this all off. And it's one. So I guess I did. So now just multiply both sides by u to the n. Yeah. And really all I need, I guess, is for you to be an element that's invertible in some ring extension containing R. Because the only thing that I really need is U inverse to be in various places. And let me give you one last piece from integrality here that we can use. Get kind of a big picture here in a moment. Using this one too. Suppose I have a family of integrally closed domains. All inverse A. Section. I do want them to all be living in some giant field somewhere, okay? Because otherwise, let me give you a couple of integral closed domains, Z mod two Z and the rational numbers, right? In this intersection doesn't make a lot of sense there. That's why I want them all to sort of live in one field. But the intersection of a family of integrally closed domains, if it makes sense to intersect them, then they're integrally closed. So, well, what are these intersection that we desire? And K quotient. And for notation purpose, it's an AI. It's quotient. What X in K. Now, suppose I have an element in K, quotient field R is integral over R. I want to show the K, I want to show that X is actually in R. Well, note that for all I, X is in Ri. K. Since X is the root of my polynomial with coefficients in K and X is in. Because I know that X is an integral, so X is a root of a harmonic polynomial with coefficients in R. X is an element of K. And it's the root of harmonic polynomial with coefficients in R. But if it's got coefficients in R, it's got coefficients in Ri. Because each Ri contains R. So since X is integral over Ri, then X is in Ri. Because each one of those Ri's are integrally closed. Therefore, X is in the intersection of all of these, which is equal to R. So R is in. Okay, any questions? Now, you might think that I'm freaking out at first, because it looks like I'm going to take a left turn. However, what I'm fixing to talk about is an incredibly intimate connection with the notion of integrality. In fact, it's a building block. How many of you go for valuations? You probably have enough in this term. How many of you have heard of the X? So there are ways to put absolute values on the rational numbers, right? There's a standard one, right, where you just kind of measure the distance as you would with a ruler, perhaps. And its completion is reals. There are infinitely many other ways, non-equivalent other ways to put an absolute value on rationals, and they correspond to every prime P. And if you use that to measure distance, as opposed to standard absolute value, and you complete it, spread that metric, then you get the PIs. So if any of you have heard that buzzword. But here we're going to talk about this in a more general setting. Valuation domains are, I'm going to talk about valuations and something called valuation domains. Let me start you off with just the definition of valuation. Here we're going to start with the field. Okay. Suppose we go to the field K. A valuation is a function B from K star, which by K star I mean the non-zero elements of K, into gamma, where gamma is a total order such that D satisfies I want you to do a couple of things for me. I want but that's like a lot of them are the value of A times B, value of A plus value of B. And two, this is, well, let me put the if all three of these are non-zero, then so it's greater than 8. The quality occurs, values are different. So what is value on what is valuation on a field? It's a way to sort of measure things. Notice that you're taking the elements K prime and you're going into gamma. What is gamma? It's a totally ordered building group. And because of the fact that gamma is totally ordered, that sort of gives us a way to measure the size. I'll give you an example of a very standard totally ordered building group, the integers, right? And so in a certain sense, when you take the value of something, it produces something positive, negative, zero, that says something about the size of the element in a certain sense. But there are other totally ordered building groups, rational numbers, real numbers, two copies of the integers ordered lexicographically, library order, 27 copies of the integers. You can go nuts with this. And I want the value of the product to be the sum of the values. So for example, if the group is the integers and the value of A is 3 and the value of B is 2, then the value of A should be 5. I like to think of that as sort of adding exponents, and with a lot of construction, you do this kind of thing. This makes for a strong triangle right here. The value of A plus B, as long as the players here are not zero, the value of A plus B is greater than or equal to the minimum of the two. How many of you have ever looked at the p-adics? You've heard of them, right? Right, okay. They're important in number theory. It's got a different geometry. In fact, geometry is too nice compared to what we used to in Euclidean space, right? So you can use these valuations to build an absolute value, a way to tell distance and metric. In the reals, it behaves the way we're used to. You've got the triangle inequality. In the p-adics, the triangle inequality is so strong that any triangle is isosceles. All triangles are isosceles. If you have a circle in the p-adics, any interior point of the circle is the center. So there are weird things that happen in the center because the triangle inequality is actually too strong. Well, two for our prejudices, I guess. Now we're going to come back to this value, but in a certain sense, you're going into a totally ordered Gaussian group. So this is doing something about measuring the size. This is, I think, kind of standard, and this right here sort of puts a little bit of control on what happens when you add two things. Now, I'm going to define something that's totally different in a certain sense. Proposition. And I'm going to use this for my definition. 922. Let P be an interval Roman. The function is okay. Following this, there's actually many more equivalent things here. These are just some of my favorites. For all non-zero, A, B, and B, A divides B, 4, B, and so. Okay, so we already know here that we're going down the road of very strong stuff, right? This means if I take any two non-zero elements out of this interval domain, this is the first definition I ever saw for this concept. One of them divides the other, right? And I remember thinking, okay, I can think of an easy example of that, a field, right? Any two non-zero elements. In fact, they both divide each other as fields. I was like, this has got to be a pretty small class of domain, right? This is a very strong condition. Two, for all U in K star, either U or U inverse is V. This is, it doesn't require much thought to see the equivalence of these two, right? Because what this says is, given A and B and B, either A over B or B over A is in B, right? And that's equivalent to this way. Three, E is 7x K such that B of x is greater than 0, union 0. So if you ever find a domain that has this property, then there is some valuation on its quotient field such that V is the set of non-negative elements of that valuation, union the zero element. Because remember, we don't make the valuation of this. By the way, let me point out that zero can be interpreted as the identity of gamma over there. And so since it's totally ordered, you have zero, you have positives, and you have negatives, right? And that's it. Obviously, everything can be compared. Let's look at some examples of this. Oh. Domain. Satisfying. One. It's all of these conditions. It's called. Uh, let me, let's look at this examples. First one, let's start with this principle here. There's always, okay, think smart aleck. Given any field, I can always find a valuation. There's always a default true valuation. You way to describe it. Zero, right? So just take the totally ordered group zero, right? And just the value of everything is zero. If you do that stupid valuation, value everything at zero, what is the valuation domain corresponding to it? B, equally proposition. It's going to be the entire portion, right? It's going to be because everything is zero and then throw the zero in. By the way, we'll kind of get through this. I'm not going to prove the equivalence 1 and 2. That's an exercise that's pretty easy. This one we'll explore as we go along. So that's my first. Okay, so any field is a valuation domain, given its trivial valuation. But how about something we need to do? Does anybody, I mean, this is a strong condition. Can anybody give an example of a valuation domain that's not a field? What's here to see? Maybe it's this. We can form a power series of fields valuation. Once you see that this is true, it's actually not so bad. Take a non-zero power series. What is it? Well, if it's non-zero, it has to have a non-zero coefficient somewhere. So AN is just the smallest, non-zero coefficient. Everybody okay with that? Now, let me do something. Seems. Say it, I know there. So that's the power series over a field. And it's got a non-zero constant. Let's see what. That's exactly right. This is a unit. It's crucial here that this is on the field. That's the leading terms in units. This is a unit. So what do we deduce from all of this? So a simple computation is any non-zero f in f power x can be written in form x to the n, u, where n is greater than or equal to 0, and u is a union in f power x. Right? Now it's easy to see its valuation. So suppose xn u1 and xm u2 are in f power x. Using the notation above, with the u1 and the u2 both units. Can somebody tell me if this is a valuation domain, one of those must divide the other? How can you tell? We'll say without loss of generality, n is less than or equal to m. So in this case, this one divides this one. X to the n u1 times x to the m minus n u2 u1 inverse m. So whichever one has the smallest x value, divides the other one. And if it's a tie, they both divide each other. Right? So this is a non-trivial example of valuation. By the way, anybody want to take a guess at what the role of gamma is being played here? What's in that? I would say order, right? But yeah. So the group that we want is the integers. And the value is, so any element of the quotient field. So note that A is the quotient. F all x. Then, well, let's see, add alpha is a non-zero element of K, then alpha is equal to x, the n, u, where u is the unit, and that power x. And this time, n is n. Because just take the quotient of two things like this, and you get the tail is something that's a unit, and your exponent is n minus n, being any integer. So here's how the valuation map will work here. It looks at alpha, it's not zero, sees what this n is, which is an integer, positive or negative, and it parses that out, right? And that's the way the response works there. Anybody think of another example? There's another one that we've seen. And I don't want to go through too many details of this, because it's, in certain sense, is very similar to what we just did. Notice if you have an arbitrary fraction, non-zeros, a non-zero fraction in the rationals, if I give you any prime, you can pull as many primes out of the top as you can, make it zero. And as many primes out of the bottom as you can, and you can cancel. So any arbitrary fraction in the rational numbers can be written as a power p, positive or negative, times a fraction where both top and bottom are relatively prime. So that's very much like this power series here, where instead of x, we now have it. This is also a valuation domain with value group Z. See if you can find one with value group Q. That's decidedly more complicated. Or value group lexicographic sum of Z and Z, two copies of Z ordered lexicographically. We might look at some of that later. See if you can tickle your brain and come up with that. Okay. Before I stampede off too much, let me give you a theorem. So I want to make some connections. I spent some time talking about the integral nuts, freak out here doing all this crazy valuation. What is this all about? Here's one of the key reasons for this. Here. Evaluate. Uh, okay. I'm gonna feel about this earlier lemma that I scoffed at the time. So let's suppose V is valuation domain. Let's suppose we go K. Okay, so suppose we have valuation domain. Let's say push fills K. Suppose alpha is an integral element, so it's integral to You have to show how much it was. So if alpha is B, we're done. So you can assume, just for distance, that alpha is not. So since V is valuation, alpha is not. What must be? Its inverse has to be. Now, since alpha is integral over alpha, then I interchanged, if you look back at that lemma, I think the conclusion we had was U inverse is integral if and only if U inverse is in RU. Just replace U inverse by alpha. Right, so U inverse must be in VU. That means alpha is in V alpha inverse. But alpha inverse is in V. So this is the contradiction between the two alpha and V. Alpha is in V. And so there you go. I like this proof also because it proves something about integrality without ever using that. So that will build up to next time. This is a good place to quit. Any questions? For being on Friday. Remember, I'm going to see somebody. I should be back in my office by 10:30. So y'all have a good one, and we will see you about Friday.